Hello, in this video we'll talk about how entropy depends on molecular structure and how we can calculate the entropy change for a reaction. So, in our previous discussions of thermodynamics, internal energy, or just energy, which we called U, and enthalpy, H, we could only measure changes. You don't know how much energy this thing has, but you can see how much energy changes when you go through a reaction. With entropy, that's not the case. You can know how much disorder is in a system. It's a much more knowable thing. And so instead of dealing with enthalpies of formation and all this kind of stuff with some arbitrary reference, we know that entropy is 0 for a perfect crystal at 0 Kelvin, and we can build everything from there. So we will put in tables something we call the standard molar entropy, which is the entropy at 25 Celsius and 1 bar, or 1 molar solute concentration if it's in solution. And then this serves the same function as the enthalpies of formation that we were dealing with earlier. This is always positive because you always have some disorder in a system, and if you're comparing it to 0 disorder, well then that change is always going to be positive. Alright, so there's some trends here that we can pick out that are good to know because I think it's helpful for understanding how this concept of entropy works. So your standard molar entropy for gases is larger than liquids, which is larger than solids. You can see this in the table because if you look at the value for water versus steam, right? Steam has a much higher standard molar entropy. The same is true for bromine gas and iodine gas. Now, if something's heavier, you have a higher standard molar entropy, because the energy levels in a bigger thing tend to be closer together, and therefore with a given amount of thermal energy you can distribute that energy between more levels, which is more disorder in a way. So if you compare, for example, like bromine gas and iodine gas, iodine is the heavier element or molecule, and thus it has a higher absolute entropy. Also, if your molecule is larger, the entropy is greater because there's just more ways to distribute energy such as vibrational energy throughout the molecule, because there's more bonds, more ways to wiggle, and things like that. And so if you compare methane and ethane down here, right, ethane is the bigger molecule and it has a higher entropy. All right, so definitely know this so that you can predict these kinds of things. It's good to know. All right, and then the next thing we're going to talk about is how we can use these standard molar entropies to calculate changes for a reaction. And now this is useful because we, just like we did with enthalpies, with entropy we want to know how that changes across a reaction. And then we'll tie those two together into something we call the Gibbs free energy later. That's pretty important. And so very analogously to how we did this before, you have some reaction. A plus B goes to C plus D. The lowercase letters are the stoichiometric coefficients. And so it's final minus initial, products minus reactants, gives you the entropy change for this reaction. And how you do that is you take the entropy of some substance, C, and then D, right, products, and you multiply each of those by their stoichiometric coefficients. So if you make 2 water molecules, you multiply the entropy of water by 2. That makes sense. And then you subtract from it the sum of all the products, right? So this is you're adding all the products together, and then you subtract it from the reactants. And so we write this on your info sheet like this. I don't really like writing it this way because it doesn't tell you put the coefficients in there, but I've seen equations written with put the coefficients in here, and then there's like random letters in here, and then you got to figure out what those are. So there's no good way to write this. You just have to know how to do the process. All right, so products minus reactants, and then you need to know that this is going to be multiplied, each species, by their stoichiometric coefficients, because it's not obvious from the equation, which is all you're going to get on the test. One other thing to note is that this has the degree sign on it because we are calculating the standard entropy change. And so this is 1 bar, 1 molar, 25 C. Because that's the values we start with, that's the delta S we calculate is at standard states. So it needs the degree sign. Okay, so let's do a calculation. What is the standard entropy change for this reaction? These you would find in a table, and then here's the reaction you're given. And so when you do this, you're going to go final minus initial products minus reactants. So the product here is carbon dioxide gas, and there's 2 of them. So you take the standard entropy for carbon dioxide gas, multiply it by 2, subtract from that all the reactants. You have 2 carbon monoxide molecules and just 1 oxygen. And so let's plug these numbers in here. I already multiplied this by 2. And then you get negative 233 joules per mole Kelvin. So one outcome of this here is that this shows us something general. If you make less gas molecules, your entropy change is negative, which is generally non-spontaneous unless it's outweighed by delivering a bunch of heat to the environment or something like that. And so, right, because gases are very highly entropic, if you want to say it that way, because there's many different ways to distribute the particles around. And so if you make less of that, then you're overall going to have less entropy, like pretty much guaranteed. All right, let's do one more example. So here we're taking solid ammonium chloride and turning it into ammonia gas and hydrogen chloride gas. See, I stumbled over calling it hydrochloric acid, but as a gas, you call it like a molecule and it's hydrogen chloride. All right, what is the entropy change for this reaction? So looking at it, you could probably take a good guess, going from a solid to 2 gases. But let's calculate this. So we're going to go final minus initial. So there's no stoichiometric coefficients here. That makes that easy. Here's ammonia, here's HCl. Then subtract from it the reactant. So if you plug numbers in there, you get a positive number, 285 joules per mole Kelvin. So this gets us to the converse of the rule before, that if you make more gas molecules, you're going to make more entropy. And so your overall change for the reaction is positive. And again, this is such a strong effect that it almost overrules anything else that might be going on. Now, if your total number of gas molecules doesn't change, okay, then your entropy change for the reaction can be positive, negative, but it's much smaller than if you're making gas or reacting away gas. Okay, so now we can use this as something else in our toolbox to go and take numbers out of a table and figure out entropy change for a reaction, which is super useful. So thanks for watching.